Hydraulic systems can be dangerous. Always make sure you are properly trained and follow all safety procedures before working on any hydraulic equipment. After working with hydraulic systems for over 30 years, I've seen the same mistakes happen again and again. In this video, I'll show you the most important lessons that I have learned. Lesson 1. Cavitation is not always the pump. When people hear noise in a pump, they immediately think the pump is bad. So they replace the pump, and the same problem comes right back. Most people think cavitation is just air in the pump, and yeah, air problems can cause cavitation. But that's not what cavitation really is. Cavitation happens when the pressure inside the pump drops so low that the oil actually starts to boil, forming tiny vapor bubbles. And when those bubbles collapse, they hit hard, causing noise, vibration, and real damage inside the pump. Sometimes the pump really is the problem, but what if it isn't? And more importantly, how do you know the difference? In many cases, the suction filter, usually around 120 microns, gets clogged with dirt and contamination. That creates a restriction on the suction side, and that's what leads to cavitation. Most of the time, this happens because of poor filtration or lack of preventive maintenance. And the problem is, these filters are usually buried at the bottom of the tank, so they're not easy to check. One thing I've learned, real understanding comes from knowing how something actually works, not just following steps. That's actually one of the reasons I like using Brilliant. Brilliant is a learning platform that helps you get better at math, coding, and problem solving, using step-by-step interactive lessons. You're not just watching videos. You're solving problems, adjusting things, and seeing how the system reacts in real time. For example, their digital circuits course is solid. It shows you how digital circuits work step by step, instead of just memorizing it. Which is the same mindset you need when working with digital circuits, tracing the logic through each gate to see where the signal breaks down. The courses are built by experts from MIT, Harvard, and Stanford, and they're designed for anyone, whether you're just starting or already experienced. You start with the fundamentals, build them up step by step, and move into more advanced concepts. To start learning for free for 30 days, go to brilliant.org/electricalad, scan the QR code on the screen, or use the link in the description. You'll also get 20% off an annual premium subscription with full access to all courses. In larger systems, we sometimes use an external suction filter because it's easier to maintain. But since it's not submerged in oil, it can pull in air if the lid or fittings aren't sealed properly. When that happens, air gets into the pump, pressure becomes unstable, bubbles form, and that can lead to cavitation. Another cause of cavitation is misalignment between the pump and motor, especially on larger setups without a C-face mount. When the alignment is off, it puts stress on the shaft seal, and that can let air get pulled into the pump. Once air gets into the oil, you start getting bubbles, unstable flow, and that can lead to cavitation. To prevent this, you should use a laser alignment system to make sure the pump and motor are properly aligned. On larger pumps, even a small misalignment can cause serious problems over time. Lesson 2. Pipe failures caused by valve shifting. In high-pressure systems, when a valve shifts quickly, the system can go from low pressure to full pressure in milliseconds. This rapid change creates what's known as hydraulic shock, a sudden pressure spike in the piping. In some cases, you can actually see the pipes move or jerk, even when they're clamped. Over time, this repeated hydraulic shock can crack welds and eventually damage the piping. So how do you prevent hydraulic shock? The best way to control hydraulic shock is to install a properly sized bladder-type accumulator on the pressure side of the system. Set the precharge to about 60 to 80% of system pressure and place it as close as possible to the source of the shock. Another way to reduce hydraulic shock is to replace a short section of rigid piping near the source of the shock with a properly rated high-pressure hose. The hose can expand slightly under pressure, which helps dampen the pressure spike. However, the rigid piping on both sides must be properly supported and clamped to a solid structure to prevent movement, vibration, and additional stress on the system. If you're not familiar with hydraulic symbols or how to read a schematic, I recommend watching my other video, 30 Years of Hydraulics in 17 Minutes, before diving into this one. I've also added some helpful resources in the video description if you want to learn more. Lesson 3. More pressure does not mean more flow. This is one of the most common misunderstandings in hydraulics. Many technicians and operators mistakenly crank up the pressure setting, thinking it will make the actuator move faster. But here's the truth. Pressure does not control speed. Let's say your system is lifting a 10,000-pound load. It takes 800 psi to lift it, and your relief valve is set at 1,000 psi. When you shift the valve, the gauge shows 800 psi, not 1,000. Why? Because the system only builds the pressure needed to move the load. The relief valve doesn't open because the pressure never reaches its setting. It's just a safety backup, not something that controls normal operation. Now let's say the cylinder is moving slow. So someone increases the relief valve setting from 1,000 to 1,200 psi. But when the system runs, the pressure still stays at 800 psi, and the speed? Still slow. Why? Because pressure has nothing to do with speed. Flow does. And even if the load did need 1,200 psi, raising the pressure limit still won't change the speed. It helps to lift the load at the same slow speed. Not unless you increase the flow rate. So, why might flow be low? There are a few common reasons. The pump is undersized, worn out, or just not putting out enough flow. The pressure filter might be clogged, restricting flow to the system. Or a flow control valve is set too low and limiting the actuator speed. Always fix the flow issue first and do not touch the pressure setting. Lesson 4. Misunderstanding relief valves. Relief valves are one of the most misunderstood components. Many people think they control the system, but they don't. A relief valve is a safety device. Its job is to protect the system from overpressure. When the pressure rises above a set limit, the valve opens and diverts flow back to the tank, preventing damage to components like pumps, hoses, and valves. In larger systems, you will sometimes see two relief valves for protection. The main relief handles normal overpressure, but if it fails, the secondary relief takes over. That backup valve is usually set about 15 to 20% higher, so it only comes in when something goes wrong and prevents the system from damaging itself. Lesson 5. Unguided loads destroy hydraulic cylinders. Another hidden failure I've seen many times is rigidly mounted cylinders handling loads that are not properly guided. A hydraulic cylinder is designed to move a load, not to guide it or support side forces. When the load is not guided properly, all that side force goes directly into the cylinder. This creates side loading on the packing and the seal, and over time the cylinder will start to leak and eventually fail. In properly designed systems, like presses, the load is always guided, so the cylinder stays aligned and doesn't see side loading. In cases where the load cannot be guided, a clevis-mounted cylinder should be used. The clevis allows the cylinder to pivot slightly, which accommodates movement and helps eliminate side loading on the rod and seals. However, the rod size and cylinder design must be selected carefully for that type of mounting. That's outside the scope of this video, but the cylinder manufacturer can help you choose the correct size and type. Lesson 6. Overhung load. I've made this mistake many times, especially with newer engineers, thinking that a flow control valve is enough to handle an overhung load. Let's talk about overhung loads. Unlike horizontal loads, you can't use the same circuit design for overhung loads because gravity plays a major role here. Imagine a 5,000 pounds load hanging from a cylinder in this example. When the directional valve is energized to lower the load, it free falls, much like dropping a heavy stone from the top of a mountain. This happens because the rod end of the cylinder's port shifts to the tank with no resistance to counteract the gravitational force. You might wonder, why not use a flow control to slow the free fall? The problem is, if you reduce the flow too much, it builds up high pressure at the rod end of the cylinder, which can damage the packing. To exaggerate this, imagine the flow control is fully closed. The pressure could skyrocket to 1,000 psi, plus the full weight of the load bearing down. With nowhere for the oil to go, all that force piles up on the packing like a pressure cooker ready to explode, eventually causing it to fail. So, how do we solve this problem? The solution is coming up next. The answer is a counterbalance valve. It's a normally closed pressure control valve designed to balance or counteract a load. The pressure is usually set to create a force equal to or slightly greater than the overhung weight. This pressure is calculated based on the rod end piston area and the weight of the load. If you have any questions about counterbalance valves or how to calculate the pressure settings, feel free to drop me a note in the comments. Lesson 7. Poor filtration destroys hydraulic systems. Even small particles in the oil can cause serious damage over time. Directional valves rely on precise metal-to-metal surfaces. If metal particles get into the oil, they can scratch those surfaces, leading to internal leakage and poor valve performance. At a minimum, a properly designed hydraulic system should have 2 filters, a suction filter and a return line filter. The suction filter protects the pump by preventing large contaminants from entering the system, and the return filter cleans the oil before it goes back into the tank, removing contamination generated during operation. In systems with multiple directional valves, and especially with proportional or servo valves, a pressure line filter is often required. This filter cleans the oil under pressure before it reaches the valves, protecting those precision components from contamination. Lesson 7. Heat is the silent killer. Remember, a significant portion of the input power in a hydraulic system turns into heat. As a general rule, about 25 to 30% of the horsepower is converted into heat. For example, in a 50 horsepower system, roughly 15 horsepower becomes heat, which is about 38,000 BTU per hour. In a continuous duty hydraulic system, that amount of heat can raise the oil temperature very quickly if it's not properly controlled. This amount of heat causes the oil viscosity to drop, reduces lubrication, and leads to seals hardening and eventually failing. Once that happens, the components are no longer properly protected, and wear increases rapidly throughout the system. A properly designed and reliable hydraulic system must include an effective cooling strategy. Depending on the amount of heat generated, this can be either air-cooled or water-cooled. If the system is running continuously under high load and operating temperatures remain elevated, then a dedicated cooling system is not optional. It becomes essential. In these cases, a properly engineered heat exchanger should be selected and sized correctly for the application. Manufacturers of heat exchangers can assist with proper thermal design and selection to ensure the system stays within safe operating limits. If you found this video helpful, don't forget to hit the like button, subscribe to Electrical Lad, and turn on the notification bell so you don't miss the next video. Thanks for watching, and I'll see you in the next one.